Alright, so next we're going to go from the inner core, we're going to go to the outer core. And unlike the inner core that is completely solid, the outer core is liquid. And it's completely molten. Yet it's the same exact percentages. Okay, it's still 80% iron and 20% nickel. We're just molten rather than solid. And because it's molten, it gets to move. And for those of you guys don't understand even the slightest bit about electricity, you'll understand that the easiest way to create an electrical field or a magnetic field is to basically take a wire and wrap it around a magnet and spin it. Well, that's basically what we've done. The inner core acts like a magnet. And then the outer core is this liquid that's spinning around the magnet, and that actually generates our magnetic field. And that's what we're going to talk about on Monday with magnetosphere. Okay, so that's your magnetic field going around. So, so the rotation of that outer core actually creates the magnetic fields of Earth. And those magnetic fields of Earth are really important because they protect us from the sun's cosmic rays. And those are really nasty rays. If you want to talk to you guys about what happens when those things actually come in contact with your body. So that's the outer core. Then we move to the mantle. There's a lot going on in the mantle. It's big, it's thick, it's hot. It's mostly molten. And it's pretty much the entire Earth, okay? It's 80% of the volume of Earth. And that's a very significant percentage of Earth is all on our mantle. And the mantle, for the most part, is almost half of the Earth's radius. So it's almost 2,000 miles thick. And so at this point, that heat from the core, remember we talked about that heat moving away from the core, moving out to the crust. Well, in the mantle, we get these convection currents. Someone explain to me how convection works. This is always interesting because I get this as a test question and I get the same answer every single time. I get the definition of convection. I don't want the definition. I want somebody to explain to me how convection works. And we have a lava lamp at home. Explain to me how the lava lamp works.
Well, the lava sits at the bottom of the lamp.
Okay.
And then turn the light on.
Okay.
And it heats up the lava, and the lava goes up. And then back down.
Why does it go back down?
Because it got
It cooled. Guys, when you look at your lava lamp, it's the convection currents at a miniature scale. What you have is heat from the inner core. And it's heating up the stuff in the mantle. As things become heated, I want you to think about this for a minute. I want you to think about some really simple things. As things become heated, what happens to their volume? Okay. No, weird. What their volume does. Volume does what? Something gets heated, what happens to the volume? It expands. But the mass stays the same, right? Okay? I want you so that, let's do a little bit of math work here. I know for a lot of you guys this is a struggle point. This is really fun to talk about this. I want you to think about the two fractions. I want you to think about 3/4 versus 3/8. Which one's bigger? 3/4 is bigger. right? Okay, so let's say that in this case, my mass, remember density? Hold on. So density is mass over volume, correct? So in this case, both my masses are the same. Well, what happened to my volumes? My volume expanded. So what happened to my density because my volume expanded? The density decreased. Does that make sense? So when things get heated, their density actually decreases. That's why the lava flows to the top, because it's less dense than the surrounding material. So therefore it rises to the top. But once it gets away from the heat source, what happens? It starts to cool. When things cool, what do? They contract, right? And therefore, we go back from the 3/8 back to, so now what happens to your density? As I'm cooling, what happens to my density? I'm contracting my volume with the same mass. So now density is increasing. I'm going in this direction, my density is decreasing. So now as I'm cooling, my density is increasing, and therefore I'm sinking back down to the heat source. So I get heated back up, I expand once again, my density decreases, and then I rise back up to the top. Okay? This is a constant cycle, right? If you leave your lava lamp on, this wax, which they no longer use lava, I'm not sure they ever did use lava, but basically it's just a wax, and it's constantly cycling through that tube, correct? That's really what convection is all about. Something gets heated, it rises because it lowers its density. So then as it gets too far away from the heat source, it cools, contracts, falls back down to the heat source. That's all convection is. It's this rotating heat source. And then, in fact, that's the way that most of your ovens work. They're convection ovens. So they actually create a heat source and it cycles the heat. It cooks very evenly. That's why sometimes it's better to cook things in the oven than in the microwave. The microwave does not cook things evenly. And so that's one of the things to keep in mind here when we think about how convection works. Has anybody ever boiled, not an egg, actually egg, I was thinking more like noodles, but eggs. Not so much wrong, like the elbow macaroni. Okay? But eggs are actually really good. When you boil the eggs, what's really happening with the eggs at the top? What are they actually doing? You ever watch them? They roll up and down through the pan. Why is that? That's the convection current within the pot. And they're actually rolling through the convection current with the water, and the water is actually pushing them. So that's something to keep in mind there with convection currents and how they work. All right, last thing I want to mention here, basically those convection currents move the plates. So we thought about the convection currents of the eggs are moving the eggs around. The convection currents are also moving our plates around. So the reason we have plate tectonics is because we have an active core. Without the heat that's being generated in the inner core, we simply would not have plate tectonics. But without plate tectonics, we would have a very stagnant planet that would probably prevent us from being able to support life. So that's really important that we understand that. And when we look at Mars, there's almost no evidence of recent plate tectonics happening on Mars. What does that tell you about its inner core? We'll go with that phrase on, okay? So it's not working, right? It's not nearly as active as ours. And so basically Mars has cooled off quite a bit. So those are some of the things to keep in mind. This is the perspective here. Okay, now this is something